Hi, this is a KPF presentation for a project we worked on in Beijing called the BCC. And the inspiration of this project was really embedded in the urban kind of context that had a number of buildings that are adjacent to each other, but not connected. And the idea was to try to connect these buildings and to create almost like a continuous landscape. And so to do that, we had to kind of go to nature to find inspiration of how some of these karst mountains are kind of a formation of mountain that seem independent, but they also have a lot of interesting moments when they link up together. So in a sense, the in-between building become as interesting, if not more interesting, than the buildings themselves. And we try to kind of represent that in a kind of really old-fashioned technology using clay, but also in it's a very computational project in that sense, because we had to use the latest scripting and optimization tools to be able to come up with something that is buildable. So the idea of kind of a hard shell on the outside, which defines the way the building addresses the urban context, versus the soft shell on the inside, that's more to do with the actual site itself and the kind of maybe more human scale experience. And in that sense, then the project could be read as a combination of two facade types. Really, the type 1, which is we're calling the outer shell, and the type 2, which is a more organic and more fluid inner skin. We tried to rationalize it as much as possible by kind of creating a big chunks of these facades as straightforward flat facades. So all the red lines really represent these almost walls that are straight up. And then as you start to turn corners, you go to the blue lines, which are more the bowing out in most cases, and also tapering at the corners. And that bowing up and tapering created a really interesting play, but also complication that we had to resolve in terms of geometry. And notably, the key element is, or the key complication came from the corner radius that changes as you go up. And the idea was that this building is not a high building, it's a 100-meter building, and this bowing out and kind of the tapering gives it a bit more verticality. And so some corners were tapering from 7 meters to 3 meters, and some corners from 10 meters to 7 meters. And so that kind of created this different instances around the building that we had to resolve. The idea was to keep the building looking simple, and so that grid that shifts on the facade is a grid that creates alignment every 3 stories. So it's kind of, it shifts, but it realigns every 3 stories, and that gives you a continuation of lines that work really well on the building when you look at the straight part of the building. But as that module start to turn the corner, those alignment become really difficult. We wanted to maintain them, so we had to change dimensions, and some of that meant that the modules became a bit more unique as you go around the corner, and this uniqueness created a variety of panels that we had to resolve by using the rationalization tools. And also it allowed us to basically look at the building as a building that has maybe 80% very straightforward flat panels that are modeled as you see in a 3-dimensional way. But the last smaller percentage of panel is a panel that had to be rationalized. So I'll pass the presentation on here to Gokhan, my colleague, to explain how we went through the rationalization.
Thank you, Mustafa, for the introduction. Hi, everyone. This is Gokhan Ongun. I am working at KPF as an intermediate architect and a computational designer, specialized mostly on complex geometries and the post-rationalization of them, too. So my involvement to the project was right after all the design principles and the foundations of how to generate the massing and this overall look of the building were set. So basically, every single flat area and, like the logic of these filleted corners and the connection points were described. However, they didn't have a fixed dimension yet, which were coordinated with the engineers and as well as the client. So basically, what my involvement was to find the problem points, problem locations for the geometry, and rationalize them as much as possible to increase the constructability and the cost of the entire building. So in order to start the whole process, the first thing that we had to do was to generate this building and generate the massing in Grasshopper rather than having a static Rhino model that we think works. So building everything in Grasshopper gave us the capability of having the corners as parameters, having all the dimensions as parameters, and we were able to go back and forth between the different options and different methods that we were coming up with in the later process. So after generating the massing, what we have done was to do a very simple, very simple analysis of the entire facade. This is the most basic Rhino command that you can find, the surface analysis tool. And whenever we applied that after we generated the massing, we started to realize, hey, we have a problem at the corners, as we were expecting, obviously. The 80% of the building, as you can see, all the blue zones were flat or single curvature. However, the corners were the most problematic part. And after this, we were like, okay, let's check what is happening with the panels when we apply the staggering grid on top of these double curved areas. So what we realized, we were getting a really messy panel distribution, let's say. We were literally getting 587 different panels, which meant 587 different molds. So all these panels were going to be produced by molds because the material that we are using is UHPC, and this amount of molds were going to be actually much more expensive than the rest of the facade, most probably. So we had to come up with a method to tackle this entire problem. So as you can see in the graph at the middle, it literally shows the distribution of these panels in a space where we compare the dimensions and the curvature of it. It is really varying and worrying. So we had to go through another analysis for the internal facade for wall type 1, 2. All of these panels are single straight extrusions on simple arcs. However, all these arcs are different. Again, it creates a problem to describe the geometry to consultants or to constructors later on. So the first method that we came up with for the wall type 1 was to increase the flat panels and the single curvature panels as much as we can. So the length was not really an issue, apparently, and we were pushing the flat panels as much as we can to where the curvature starts or curvature ends, which reduced the amount of complexity that we were getting on those corners slightly. After this first step, we applied the staggering grid for the corners, and then we agreed on a tolerance amount with the engineers, which is 40 millimeter tolerance for the manufacturing method. This tolerance actually gave us capability to cluster all these panels into different molds, And we mainly used machine learning algorithms while doing so. The basic script that we were using was k-means clustering from Nathan Miller's Lunchbox plugin in Grasshopper. The components were really helpful in the process. As you can see, when we started to apply all these tolerances, we were able to grab multiple clusters. Actually, this was a step-by-step feedback loop, let's say. And first we were coming up with, like 165, and then whenever we introduced more and more input to the tolerances, we were able to reduce down to a logical number, which is like 65 different molds and 65 different panels that were going to be produced, which will eventually become these corners. And for the wall type 2, we had to come up with a very simple logic. Every single arc that you are seeing here were defined in Grasshopper between these buildings. So we had to come up with where this connection happens, how we can prevent having strange tangent points which coincide with the curvature coming from the corners, and then how do we create those symmetry axes to describe this geometry with less and less amount of arcs. And in the end of the process, as you can see on the left-hand side, the Tower 1 and Tower 2 connection, we were able to define only 1/4 and then repeat that 4 times, which was quite impressive for how we can deal with this connection. And it was more or less the same for the right-hand side for Tower 2 and Tower 3 connection too, with the exception of this corner. Still, we were able to carry on other dimensions from the other side of the building, so which was fine by us. And another problem that we realized, because the symmetry axes on section for wall type 1 and 2 were not merging, and it was creating a problem on the slab edges. The slab edges were not actually relaxed enough, and they were overlapping, which would create a detailing problem. So we had to merge those as well. And after that merge, we were able to relax the edges and then create a proper geometry. The shape of it changed, as you can see, from left-hand side to right-hand side, which in my opinion became a better shape. Yet it created this easy detail that we can come up with for all the slab edges. So as you can see, all the wall types that were described, wall type 1, wall type 3, wall type 2, they were all connected to each other. Whenever we changed something in the first one, it needed to affect the second one. So every single thing was living on a balance. So but after all, thanks to our computational method that we applied here, everything was easy to resolve. And as you can see, for the wall type 2, we were able to reduce the variety approximately like 60% in total, which was really impressive, because we were thinking, oh my God, this is literally a very complex geometry that we cannot describe. But after spending some time, it was good. So at the end, we described all these panels as points, and then converted all these points into Revit, and then converted all these points to Revit. And then these points has been taken with a Dynamo script, and we applied this 3D geometry on all these panels, which looks, as you can see, quite spectacular as a final result. From the starting point where the design intent was to here, we were able to maintain the intent like 95%. And hopefully this building is going to be under construction very soon. And when it's finished, we are really excited to see it in real life. And thank you for listening to us. If you have any questions, we would be really happy to answer them. And have a great rest of your day. Thank you very much. Have a great day.